Hello, I am Dr. Ahmed Abdilal, and this is the second part of the nature of sound, that is Unit 1 for speech and hearing science. In the previous segment, in the previous video, you will find an introduction, speaking about different aspects of the physics of sound and presenting concepts. So at the end of this recorded lecture, you will find questions for the first video on this unit. And also you'll find the questions for this video. You need to really take notes while you are listening. You should pause every 20 minutes, 25 minutes, review your notes, reflect on the material that you are learning. And then at the end, if you see that there's a question or something that I ask you, in the little study guide that I provide, if you see that you can't answer a question or there's a concept that you cannot kind of make sense of, then you need to go back to the explanation and listen again to the part where I discuss that concept, or there are questions and problems to solve. To find back some examples of that I provide, and that will guide you. So let us begin now, and we are going to speak in this part about combining sound waves and also various concepts that have to do with the transmission of sound, like absorption, reflection, and so on. So we ended the previous video speaking about what happens when you combine sound waves. We spoke about periodic tones or pure tones and aperiodic tones, or tones that are simply a mix-up, a whole bunch of sounds mixed up, and that there's no pattern to them. So now what happens, we'll explain again what happens when you combine two sound waves. A sound wave you can get two simple waves and play them together. They combine, they produce a complex tone. However, it is not as simple as that, because if the two tones are exactly identical in frequency and they are traveling in the same direction, like this, you have a point of compression for this wave, and the other wave point of compression that's traveling in the same direction. They push in the same direction, they combine their energy. So if their frequency is the same, and the compression is facing the same direction, and the rarefaction is facing the same direction, the only possibility for you is to keep the pitch, the frequency will exactly remain the same. The frequency will not change. However, loudness, the amplitude of that wave is going to increase. It's going to combine the amplitude of both waves. So if I'm going to give you an example. If you have two waves lined up perfectly on top of each other, and one of them, the maximum displacement is 3 decibel. At 3 decibel, like you'll find on the vertical line the decibel. So then the other wave is exactly the same wavelength, the same frequency, but when you combine it, when you look at the amplitude or the point of displacement, you will find that it is 2 decibel. So we have one that is 3 decibel, one that is 2. You check the frequency is the same. When you play the two tones together, like two people singing at the same time together, the energy in their voices will be the sum of the first displacement and the second. In other words, the first amplitude and the second. So we have 2 decibel plus 5 decibel. The resulting wave, when they combine together, because they are identical in frequency, they are going to give us a wave that is the same wavelength. However, it will have a greater amplitude. It will have a greater displacement that will raise it to 5 decibel. So, but now what happens when we take two tones that are related, however, they are not identical? So this is a situation that we see, for example, in a male voice and a female voice. So this is, let's say, this is a wave that starts here and ends here. The wavelength is from this point to that point. Then we have another wave below it. You notice that the tone starts here, but the first wave is going to end here. And if you go up, that exactly is going to be half of this wave. So the entire wave in the second and the Y wave, the entire wave fits in under one compression of this wave, the bigger wave. And then there's another wave here. So second wave begins here, and this whole entire second wave is the length of the second half of this wave, which makes the rarefaction. So now the waves are not the same. However, there is a relationship, because you could say, well, this wave is twice as long. I mean, the wavelength is twice as big as the wavelength of these two combined. Okay, so you can predict what's going to happen. They will make a pattern because they are systematically related. So what happens when we combine them? So the areas, the peaks, or the points of amplitude here, compression of the second wave, they face in the same direction as that part of compression of the first wave. So notice first that the first wave X, has a 4 decibel, 4 amplitude, or the point of displacement equals 4 decibels here. The second wave Y, has 3 decibel. That's the amplitude. So which one has more energy? Of course, the first one, because it has 1 more decibel. Now, which one is higher frequency? Higher frequency. The second one, because you have more, the tones, the waves occur more frequently in the second situation. You have 2 waves when in the 1 second, when you have, I'm sorry, you can't, I mean, but anyways, let's just represent this. You have in the same segment, you have 2 waves that equal exactly 1 of the wave X. So the parts of the compression that push in the same direction and the 2 points, these combine their energy. Okay, so there's a 3 decibel here, and this goes in the same direction as this part of the compression of this wave. So this is going to combine with this. So that piece here, that part here of this peak coincides with this, and they push in the same direction. So you say, okay, 2 decibel, this part is 2 decibel, this part is 3 decibel. That's going to give me 5 decibel. Go down, and this is where you get the 5 decibel. So it's like wind pushing in one direction, and another kind of wave of wind pushes in the same direction, and they increase the pressure or the power that they have. So this part of the wave is going to be amplified. It will be increased in loudness. Then the second part of this wave, now it is going down. This is going to coincide with this part of the wave here. So that is not a peak, this is the lower part. And that's going to be aligned to, is going to coincide with this part. So now, as a result, the loudness here of this part is 0. So this point here, because it's rest. So then you go up, and the highest, the energy in this wave goes to 4 decibel here. So 4 plus 0 gives you 4. Okay. So then we go to the opposites, to the second half of this wave Y. This is the rarefaction. It means that there isn't much air, there are not many air molecules in there. So that means it's going to absorb. It's going, if you put another wave facing in a different direction, it will absorb that energy. So it coincides with this part of the peak of this wave, this part. When this line, when this rarefaction goes back again, the molecules go back again to the deadline, to the midline. And these molecules are going to go back again to the midline. They collide, but this is gonna, some of this energy will be trapped into this pocket of rarefaction and will be canceled out. So that means this point of rarefaction here is -3. -3 doesn't mean that there is no sound. It just means that this part of the wave doesn't have energy. It's not produced by like loading it. It just produced on the effect of inertia, making the molecule swing to the opposite direction. So here, the amplitude of this and the opposite of this rarefaction is -3, and then the point that coincides with that is +2 or 2 decibel. So you go from combine 2 decibel with -3 or -3. That means that the 2 decibel will be lost, will be trapped here, and then you are going to have one negative less, which will push the molecule in the opposite direction, because this is negative already. So basically you say in mathematics, +2 added to -3 gives you a -1, and that is where this comes from. So what does this mean in real terms? It means that parts of this part of the wave, of the compression that coincided with this part of rarefaction of the second wave, they cancel out each other. But and this is the result here. You get a different point that is neither here nor here. That is the sum of both. So that's the -1. Then this part of the you go to the second wave here, beginning here, is going to behave in a similar, somewhat in a similar way, but in a kind of the reverse, a mirror image reversed. So the peak of this wave is going to coincide with the rarefaction of that wave, and if you come to the points and add them, -2 added to +3, that means you have 1 point more here. So that is going to give you that point here. That is 1 decibel. That's the outcome of adding this with that. So now we have lost some energy from this wave, from the wave Y, because it coincided with the rarefaction of the previous one. And then you have a similar, and this other side here, now the rarefaction here coincides with the rarefaction from this one, and they enhance each other. So you add -4 plus -3, you should get, let's see. No, it wouldn't be just quite. So you get -2 here, and it coincides exactly with -3, and then you get -5 here. And you create this pattern. You can see it as a pattern here, but if you look carefully, you'll find that this compression here is similar to this rarefaction here. and then you get this path. This, if you continue to play these tones, every time this is one new wave now. It's the resulting wave that results from combining these two. These two now are gone. They are mixed up into this brand new wave. And if you keep playing it, it will be repeated in exactly the same manner. And this is why this is gonna be still a pure tone, as even though it's complex, but it will continue to play in the same pattern. Every two waves combine into this shape going. So it is a complex tone, but it is periodic because you can predict it. It's going to happen exactly in the same manner, and they are systematically related so that you can calculate and say, if this goes up this way, this is going to happen this way, and you can measure it step by step. So what happens is, when you have tones that are identical in frequency, the frequency will never change when you add them up. Even if you have 1,000, 1,000,000 waves that are identical in wavelength, in frequency, in period, frequency, and wavelength, the only effect you will have when you combine them is that their energy, their amplitudes combine, and you get a louder voice or sound. So the best example of a sound wave that is pure tone or periodic is the tuning fork to tune pianos. So when you hit it, first you compress it. It will be compressed out of its place, will be compressed. Then it's going to bounce back to where it was, to the midline. It will not stop there because inertia will make it was already coming back moving, and elasticity is at zero. Then the inertia will cause the tine of the tuning fork to swing in the opposite direction to make rarefaction. And that is going to be continuous. So here's a compression and rarefaction, compression and rarefaction repeatedly. And each tine is going to move in the same way. Even though the second tine is one that you did not hit, we will understand that it will sympathize with the first one that you hit, and they will start to vibrate together in the same manner. And we'll explain this. So again, when you combine two periodic tones, you will have the amplitude will be enhanced 100% if the two waves have exactly the same wavelength. The frequency will not change, but the amplitude or the loudness is gonna be the outcome of both combined. If the two waves are related somehow, like one wave is one half of the other, or one wave is 3 times less than the other, then you can predict when you play them together, they will give you exactly the same pattern as you keep going. So they will still be periodic, but they will be complex. They will produce a different pattern that you need to be able to understand based on the mathematics of that combination. So when you combine aperiodic sounds, aperiodic, make sure the A is attached to the P, means the opposite of periodic. Then you have no pattern. You have a random pattern. I'm sorry, because pattern is predictable and it is not random. So random means you cannot predict it. So random is the opposite of pattern. So in the aperiodic, they do not combine. When they combine, they do not give you a pure tone, and they can never produce harmonics. I said that before, but what are harmonics? So we'll discuss that today. So think first, I'll give you some examples. We use, again, things that you can visualize, that you can see. The lake is still. The surface of the lake is just, say, motionless. Nothing is happening. You take a little stone and throw it in the river. the initial impact, the energy that this stone is going to give to the lake or cause the change in the lake, when it hits the water, the circle around the rock, the stone from all sides is going to be just, all the molecules will be pushed away. As they get pushed away, they create a circle around them. Now, where will the water go? Because you push away some water, it's going to collide against other molecules of water that is behind them and around them, and it will push them away. They get displaced. So this water is going to be displaced in a circle because of the pressure from the water around that circle. That is going to make the water just expand in the air. It will rise. When the water rises, it is going to create that peak, that compression. And then next to it, immediately as it goes down again, it will not come to the way it was before. It will sink down. When it sinks down, the water around it is going to be higher. So then, after that water around the stone sinks down, it's going to bounce back up again. So as it keeps doing this, it will be hitting the outer column and a second column that will be pushed away to make another eddy another circle around the first one, another wave. So as this keeps continuously being done, now the energy that you put is simply the stone just falls once, and it creates that initial circle that makes the biggest splash. And that circle, after the effect of that wave you created initially, it will use that energy and it will cause additional waves. Even though all the other waves that happen were not really directly caused by the stone falling. They are caused by the first wave that is created by the stone falling into the water. So the first wave, that is here, the line, by the way, is continuous. So the first wave, that we created by throwing the stone into the water, it creates the loudest sound. It makes, it's the greatest amplitude. It's the highest amplitude. So in addition, it creates the lowest pitch. That wave is going to be, when the water gets displaced, it goes far away from the stone as it is falling, because all the energy is going to be focused there. Then the stone is gone, and that wave is going to cause additional waves continuously going on and on and on, and these waves become smaller and smaller and smaller and smaller until you go to the farthest circle that is created, and the waves have become just small, and then there are areas beyond that are not even affected by that wave. So at the very, very far edges, outer, the wave front. So let's take another idea, the guitar string. You take a guitar string and you pluck it once and let go of it. Now you gave it all the energy that you need just once. You just load it by taking it away, let it go, and that's it. The first time that this guitar string is going to be coming back down to make a wave, the entire string by itself as one piece is going to go down to the midline again. It will bounce further from the midline on the opposite side. It gives you a rarefaction on the other side. That is the biggest wave that you can make with that string the first time. Now you are not going to interfere. You will not put anything else added to that. Now that wave is going to now cause a second wave. When it plays again, the string is going to play again. It will not travel as far away as far as you had originally, displaced it. So the first wave is produced directly by the energy that we put, and that is called the fundamental frequency. It's like the mother of all the frequencies that come after it. Now that has been produced. Then no more energy is added to the wave. Now the string is going to continue to swing back and forth, but the second time it's going to go back and forth, it cannot produce more than half, it cannot travel more than half of the distance of the original vibration. That means the frequency is going to be lower, higher, because the first string is going to all of it will be displaced. Now as it goes back down as one piece. Now the second time it goes, half of the string is going to start to make a wave by itself, and the second half will make a wave by itself. And you will see it. There's a video that shows you how this works. So, and just to be brief and to the point, the first wave that is produced by direct energy, by that you put the energy in, like that wave around the stone or the guitar string when you move it the first time, that is your fundamental frequency. Then the second wave that comes after it has to be, physically, it will always be double the frequency. It will be half of the space, half of the wavelength that will be traveled, and the frequency, because you are going to be able to make more journeys now. By that, you're gonna raise the frequency, and you will make smaller waves as you continue, and the waves become smaller and smaller as you go away until they die down. So all these waves that occur after the fundamental frequency, these are called harmonics. Harmonics. They occur as a result of the original vibration. So now, how to calculate harmonics? It is both easy and tricky. So pay attention closely here and know how to calculate them. So we say, which is the first harmonic? Harmonic is the sound that occurs in response to the first original vibration. So which is the second harmonic? The first harmonic. The first harmonic will be bar number 2. Okay, bar number 2. That's harmonic number 1. You can call it R1. The second vibration that is going to occur, the second harmonic here is going to be bar 3, and then 4, 5, 6, and you keep going. So when you look at this and you try to calculate, think about these together as combined, as one series. So you say, okay, I want to do some calculations. I want to know what is the frequency, what is the pitch of the second harmonic. So you say, oh, where is the second harmonic? Oh, well, the second, just ignore the fundamental frequency, because that's the original. You put energy in this. The second harmonic is the one that occurs without you putting additional energy. The first harmonic, So that is bar 1. Number 2 is the first harmonic. Number 3 is the second harmonic. Bar number 4 is the third harmonic, and so on. But in order to calculate, it will be easy to number them as in the series, because all of them are related. Number them as vibration 1, vibration 2, vibration 3, and 4, and so on. So we say, when you calculate, say, okay, this is the fundamental frequency. This is bar number 1. and like the mother goose, and these are the goslings. The second bar in the series is the first harmonic. So I want to calculate, and find out what is the frequency of the second, third, the first harmonic, second, and so on. So by nature, the fundamental frequency, say if it is 100 hertz, by nature, the first harmonic that occurs is going to be, that harmonic is going to be double the frequency, because it will be half of the distance that will travel, travel up, So if this is 100 hertz, immediately the second harmonic, the first harmonic that will result is going to be 200 hertz. But what about the second harmonic, bar number 3? What is that going to be like? To calculate it, you have to go back to the fundamental frequency and say, oh, the fundamental frequency is 100 hertz. So if I go here and get to this bar here, I'm going to go count the lines and say, well, let's see how many vibrations anyways we have. So 1, 2, 3. So 3 times 100 is going to give me 300. So you see how when the calculations now, when you try to figure the calculations, you have to basically get every one of these bars and they say times the original vibration. So please do not make the mistake between where the first harmonic is or where the fundamental frequency is. When you calculate in a series, all of them are related when they combine together and play at the same time. All of them will combine in a systematic way with the fundamental frequency. So to calculate any harmonic, first you need to know this is first harmonic, bar 2. Second harmonic is bar 3. Third harmonic is bar 4. Let's know, okay, let's see the third harmonic. What is the value? What is the frequency of that? You say, okay, well, the third harmonic is basically, in reality, the fourth in the series. So okay, 4 times 100 is going to give me 400. Well, the fourth harmonic. Oh, that is not bar number 5. So 5 times 100 is going to give me 500. And it goes on and on this way. So just know the trick in that. Know the difference between which one is the first harmonic and which one is the second vibration in the series. Okay? And this is why we have these numbers. When you make the series, all of them will combine. And if you want to figure one out, then you have to go back and say, figure out which harmonic you are speaking about, reduce the number by 1, and say times 100. So we'll do a couple of more examples. So harmonics are represented on a chart called a line spectrum that you saw, a line spectrum. And in the line spectrum, you plot all the harmonics, including the fundamental frequency, and you label the fundamental frequency as 1. It's just 1 vibration, 2 vibrations, and so on, regardless. But if you speak about another kind of, in terms of which one is the harmonic, which one is the original, this is F0, and this is R1, 2, 3, 4, and so on. So when you calculate, again, keep in mind that the fundamental frequency is always has the lowest frequency. It means it's the loudest because it is loaded with the energy that you put into it. And then every subsequent frequency that comes after it, the first vibration that occurs as a result, has to be half of the distance or half of the wavelength, and it has to be double the frequency. That is just universal. Then, so because the energy on that wave, as it keeps going away from the source, now it decreases because of damping. It decreases in a systematic manner, in a systematic pattern, like that wave that keeps, or the swing, when you let go, you pull it way far, you let go, and it goes away, it comes back to you, but the next wave, when it comes back, it will come half of the distance only. And then it keeps decreasing and decreasing in distance, but it will make more and more and more by cycles. And this is where, as it goes far, far away, the energy decreases. The distance that the wave is going to have in wavelength is going to be shorter, and there will be more vibrations in 1 second. So this is a visual that you can see on how the person in the video is going to help you see these harmonics as they occur on a string. The first vibration, the entire string is going to just go back and forth once, and then the second time it goes, it will split in the middle, and then half of it will make one wave, and the second half will make another wave. So now we have two the resulting, the first harmonic is going to be these two waves. Then as the string continues to play, each wave that is 2 feet, 2 feet, if it's 4 feet, then you have that is going to swing back and forth, it will be reduced further. Then the third time, the string is going to go back, it will be splitting into 3 segments, 3 little waves. So 1/3 of the string will make another wave, and 1/3, 1/3. You have 3. If you go and watch the 4th time that it comes, it will make 4 little waves, and it keeps playing on and on and on until that it will be segmented into tiny, very tiny pieces that each one is going to make a wave by itself, and then the string will stop. So again, just keep in mind, even though the first harmonic is the first to result from the fundamental frequency, when we count the bars in the frequencies, we count right number 1, because this is the one vibration in the series, the first vibration, then the second, third, and so on. So in that regard, when you try to calculate the first or second or third harmonic, just decrease the number by 1, and then times whatever frequency you get, the fundamental. Let's do some exercises and use these examples, because I'm going to put some exercises on Blackboard. So use this to help you figure out how to solve problems. First, we have a guitar string that is 100 hertz. What is the first harmonic? That is what I used here. So we said if this is fundamental frequency of 100, by law, the first line, the second line here, the first occurrence as a result is this bar. That will be double. It will be twice as high in frequency. So this is 100. This has to be 200, and all the other frequencies come as whole multiple integers that are, you calculate them with reference to the fundamental frequency. So you go and say, okay, here's the first harmonic, second, third, fourth harmonic. What is the value? Fourth, that is the number 5. So I'm gonna make this as vibration number 5. So it will be 5 times 100. It gives me 500. Second, the fundamental frequency of a vocal fold is 300 hertz, vibrates 300 times per second. What is the second harmonic? What is the third harmonic, the 4th, and the 10th? So let's go back. So we said this is the first harmonic. The fundamental was 300. So we said that the first harmonic, by nature, by law, it has to be double. So if this is 300, this will be 600 hertz. So the first harmonic will be 600. What about the second harmonic? Second harmonic is bar number 3. That is going to be 3 times 300. That's going to give us 900. What about the third harmonic? So, oh, this is bar number 4. So that means 4 times 300 gives me 1200. And you keep going on and on. Just know the little trick that numbering them is different than who they are. The sixth harmonic of a series is 875. What is the fundamental frequency? You just do it the same way. You're going to need a calculator here. And of course, you are welcome to use a calculator, and you should. Okay, so complex aperiodic tones. When you combine them together, you do not have a pattern because they are not systematically related. You cannot predict how they will be, and they're just random. We call that noise, because all noises are a result of combined, periods of all different patterns, and they give you that random vibration. So they have no musical tune, and they're considered as noise. As a matter of fact, you later are going to learn that the auditory cortex and the superior temporal gyrus of the temporal lobe, that has a map in it, and the only way for that map to connect is for the person to listen to every vibration, every tone that is possible out there, from 20 to 20,000 hertz. And every segment of that, if you think about it like a finger, the first segment, the first part, the anterior part, is specialized in the lowest frequencies, 20 hertz. And you keep going back, and then becomes higher and higher and higher until you reach the caudal end, or the end of it. It's going to respond, will process vibrations that are 20,000 hertz. So this is called tonotopic organization of the auditory cortex. However, in order to make it develop normally, to make it, receive the sound normally, you have to stimulate the neurons. As you keep stimulating them, they keep connecting and establishing that network that will enable you to hear a sound, immediately figure out what it is, how loud, and so on. So if the person listens to a lot of noise exposure early in life, before the map is formed and done right, that is going to cause auditory processing problems because these areas will not be receiving the adequate stimulation, and the distortion that will occur can cause long-term damage. So how do we make sense of this and relate it to, producing speech? First, speech is a stream of sounds that are periodic and aperiodic. So periodic, look at the vocal folds. My vocal folds, every time I say ah, they are going to vibrate in a predictable manner, in a irregular kind of pure tones. So when you make vowels, all vowels are made by pure tones, periodic sounds. So now when I ask you in the exam, give me examples of pure sounds that are completely 100 pure tones. Name 5 sounds. You need to know your vowels, 14 vowels in English. So for example, e, u, o. Any vowel that you name is periodic, pure tone. So then the aperiodic sounds, the aperiodic sounds are all consonants. So consonants, the only way you can produce them is to either have them completely aperiodic, complete noise, not from the vocal folds, or a combination of noises and periodic tones. So again, vowels are pure tone, no discussion about that. So if I ask you, when I ask you, give me some examples of sounds that are completely periodic, you need to think vowels, and you should know all your vowels. So when you think about vowels, don't think about letters. There are 14 vowels in English again. Say a, for example, a, oo, o, all of these are vowels. So there are 14 of them. If you haven't studied phonetics, you will do that. Then we have consonants, and these consonants are produced as a either in two ways, two kinds of them. Either as a combination of periodic and aperiodic, or completely aperiodic. So the completely aperiodic sounds are called voiceless sounds. If you recall from your AMP, when the vocal folds vibrate, they make pure tones. They vibrate when, for example, you make a sound like ah. Now, when you make a sound like s, as in Sam, you can hold your larynx here, or put your finger on your that little V notch over there, and say s. You should not feel any vibration. There is no activity whatsoever in the vocal folds. So that is an aperiodic sound made by noises in the oral cavity. Anything in the oral cavity will not produce harmonic tones. It will be noises. It will be aperiodic. So that is purely aperiodic. I'm going to give you these sounds now so that you know how to provide sounds in the exams or quizzes. That when I say sounds that are made completely with aperiodic tones. So, in addition, before this, I'm going to explain the aperiodic ones, and then I'll walk you through all the sounds, the consonants. Aperiodic is going to involve vocal fold vibration and some kind of obstruction somewhere around the oral cavity. So, like when you say zzz, now when you make zzz, you have the S that you made here first, but you only add the vibration from the vocal folds. There are two exactly. You put the tongue in the same location, you position your lips, everything in the same location. And the only difference is that the vocal folds are active. They vibrate for the z. So we call z a voiced consonant, voiced sound. Okay? So a lot of these sounds come in pairs, and then we divide them into voiceless, and voiced. Many of them come in pairs like that. So let me walk you through so that you will be able to give examples. Come from the lips and go backwards. So from the lips, you can make the f, as in fun. Test it, and the vocal folds are not going to be active. So f is voiceless. F. When you go activate the vocal folds, now you get the v. That is a combination of periodic and aperiodic. That we call this voiced consonant. Okay? So then we go as in thin, or thumb. That is aperiodic or voiceless. And then we go them or feather. Th, voiceless, as in bath. The, as in feather, that is voiced. Then go up and say s, voiceless, z, voiced. Then t, t, voiceless, d, voiced. And l, voiced, voiced. These don't have, they come only in one form. So l has vocal fold vibration, and then obstruction, that is periodic and aperiodic. Vocal fold, actually as a vowel, as a consonant, as in ring. That is aperiodic, periodic, aperiodic. But in certain cases, the is going to make a vowel. And again, we're not going to get into this. So when you look at sounds like k, 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 that is aperiodic, voiceless, and g, periodic or voiced. So then just make sure to be able to give sufficient examples of these sounds as I explained them. Then we go over the some concepts that have to do with the physics of sound. It may be good to pause the video now for a minute and then come back to it. You just take a little break. So we start with absorption. Absorption, the way it works in sound is exactly the same way it works with water or with any kind of thing. So let's say you have some drops of water. For example, you spill some water on a surface. When you have a tissue, place it on the water and let it there, for a little bit. It is going to absorb all that water. The water is going to be there. It's not going to just, go away. It will be going into that napkin or tissue, because that tissue is made where it has a lot of pores, a lot of holes, air space. And when you put that there, the water will go from no water to the area, from water to the area that has no water. And this will be absorbed completely in here. Because the only way you can do this is that when this was invented, it has a lot of air space in it. It has a lot of holes so that it can absorb. Now, if I get a piece of paper, a shiny piece of paper, and I'm going to, there's water, I'm going to put it there. It is not going to absorb as much because it is more dense. It doesn't have as many holes in it. If I get a piece of plastic, it will not absorb any water. If I get a piece of glass, so surfaces are going to absorb in different ways. And this is where this relates to us is when we look at sound insulations, for example. You say a booth that you use for audiology. When you look at the doors and the walls, they have very specialized kind of foam insulation inside that is going to create a barrier so that the sound will not completely 100% be out. There's no chance you can create a space that has no sound at all. But it is sound insulated. So the first thing, let's look at the incident wave. And then we'll discuss how this happens, what happens to the wave. So you are here, and you make a sound, and that sound, when it hits a barrier like a wall, a tree, some physical barrier, that is going to be called an incident wave, period. It stops there. So an incident wave is a wave that hits a barrier, and that's it. We don't care what happens to the afterwards, what happens to the barrier. This is the definition. So now, what happens is that incident wave can either be reflected back to you, or it can be absorbed, or part of it can be absorbed and part will be sent back. So the reflected wave is going to travel in the opposite direction, and it will combine with the original wave. If the distance between you and the barrier is short, the waves will be almost the same length. So you keep speak, and they hit the wall, come back, and they combine in space in exactly the same manner. And this way, your voice, you do not feel a difference, But if you have a big auditorium, big hallway, like a huge auditorium, and you say something, your voice is going to travel way far and hits, the barrier, the walls around. And by the time it comes back to you, your voice has already stopped. So that is going to come back either as an echo or reverb and so on. So the wave, the parts of the wave or the wave that doesn't get back will be absorbed by the barrier, and that is determined by the nature of the barrier that the wave hits. So the barrier that is smooth, a smooth surface that doesn't have pores, that is solid, is going to reflect most of the wave back. And the barrier that is porous and it has holes and it has a lot of spaces, it will trap and dampen a lot of the sound wave to various degrees depending on how porous it is or how soft it is. I'll give you an example. If you ever have a room, you are doing, say you have a room and you put the sheetrock and you go in and just speak in that room. Your voice is just dull and it is, almost muffled. It's not vibrant. But then you go and paint the room. So when you paint the room, the paint, the only way the paint can stick onto the sheetrock is that the sheetrock is made to have a lot of holes. And then when you put the paint, the holes absorb that paint and grab it and hold onto it, make it stay. But can you do this on a whiteboard? Can you go get a bunch of paint and just, put them on the whiteboard? The regular paint that you and I use, it's not going to stick. It's going to be slipping down. It will not stick because that surface is very smooth and it has no holes for the paint to stick to be absorbed by that. But so back to the sheetrock, after you paint it, the paint is going to plug in all these tiny holes, or for the most part. When you go into the room, then after the room is painted and you speak, your voice will be vibrant. It will be really nicely enhanced because there will be less absorption. If you wonder when people go to a musical concert, they wear these shiny things and shiny clothes that are like so shiny and suits that are shining. They put a lot of oils in their hair and this and that. And the purpose of this originally was so that the clothes you are wearing is going to be reflecting the sound back. It will not affect the transmission of the sound of the singers or the speakers. But if all of you go in with fluffy hair and you go curly fluffy hair and you wear fur coats or coats that are just a lot fuzzy and fluffy, and then the person is going to be speaking, that person could have a voice disorder because a lot of the sound waves will be absorbed by, especially if you add a carpet there that is also fluffy, and you have a ceiling that that has a lot of holes and stuff, that it will be very hard for people to hear, and a lot of the sound energy will be absorbed. So the extent to which a wave is absorbed, or parts of the wave is absorbed or reflected, 100% depends on the surface that this transient incident wave is going to hit. So sound reflection, the reflection is basically the bouncing back of the wave that is transmitting. It bounces back to its source. And the parts that are not absorbed will be reflected back. So in terms of the speed of sound, first, the speed of sound is the same. It doesn't change for anyone. All sounds travel at the same speed. So there's a sound constant that is 331 meters per second. 331 meters per second at sea level, at freezing temperature. That is the sound constant. Anytime that you increase the temperature beyond freezing, that means that the air is going to rise more. It will increase the distance between air molecules. And these are air molecules, when they collide together, they are going to push each other farther away. That means that in hot air, because it's traveling, the air molecules are spinning at a wider distance. In hot air, the sound will travel faster. But you can predict it. Every time you increase the temperature by a certain level, like say by 1 centigrade, then you are going to increase the speed of the sound travel by 0.6 meters per second. So you can calculate this in a systematic, predictable way. In terms of refraction, refraction is basically a change in the direction of the sound wave because of temperature differentials, temperature differences. So let's take an example. Say the air near the surface, near us, and here near the ground, is warm. So as you keep rising up in the atmosphere, the air becomes cooler and cooler by nature. So the sound waves, as they, if you and I are, say, in a desert or in a field and we speak, there's one direct path that the wave is going to travel. You are standing at a distance, and the one part of the wave is going to travel in more than one direction. It will travel to you, and then because the air is warmer. Actually, I reversed it. Actually, the water, this is the air is gonna travel in that case when we are far away, like say on regular land. The air becomes cooler. So when I speak with you, my voice is gonna come directly to you, and it will be kind of deflected down, so that the easiest path for it is to come towards you in a straight line. However, when you take that situation, say on the surface of a lake, that situation becomes different. The surface of the lake is going to, because the water temperature is lower than the outside temperature, the surface of the lake, you can think about it like a ball, like this. As you go from the edges, you have thinner water, shallow water, that becomes warmer, it is warmer. And the deeper you go into the water, the colder it becomes. So now the air that is touching the surface of the lake is going to have a particular pattern based on the depth of that lake. So, for example, here you are going to find that the air on the edges of the lake is a little bit warmer. So that as you keep going, you create now as you keep close to the center of the lake, you create colder and colder air, and that is going to be, that colder air, there will be like a pocket of cool air, and above it, there will be pockets of hot air. So that is going to create this situation now. The sound, if you go on one side of the lake, and you can get that phenomenon, it is known. If you are on one side of a lake and another person on the other side, and at night, the sound just travels. You hear a lot of sounds that you wouldn't normally hear, during the day because of the noises. So the sound is going to travel first in one way through one side, from one side to the other. That is going to be slower because of the cool air here. But then it continues to be traveling through the additional source, and as it keeps passing the air pocket, it will curve and go through the hotter air above the lake, but it will be curved like this. And that is going to cause the sound to be reflected back again to the same listener. And that is going to enhance the sounds coming from the other side. So that is basically refraction, and it has to do with differences in the temperature of the air in different locations. Diffraction. Diffraction is change in the direction of a wave that is traveling through an opening or around an obstacle. So, for example, if you have a wall and make a wall, and make a hole in that wall, and you stand behind that hole and call someone's name, hello, the sound wave is going to be spreading in different directions. It will bend in different directions, and it will be repeated. It create multiples of these sound waves that combine together to make the sound louder. And this is where the invention of the microphone or the what do you call it, the megaphone is. So you can I can create one simply by making a cone like this, and I make a hole here and I speak hello, hello. So that is going to create the diffraction. That will increase the wavelength, and it will make the waves longer, and they will be louder, because any wave that is lower frequency, the lower the wave is in frequency, it means the greater the wavelength, and it means that wave is going to travel a longer distance. It will be louder. Interference here can be positive or negative. When we speak about sound, it means the combination of sound waves when you combine them. No judgment. We don't know if that could be negative, that could be positive. So when a sound waves combine, they interfere with each other in positive ways. Either positively, we call this positive interference, or negatively, we call this negative interference. If the two waves are too different and you play them at the same time, they interfere in a way as they cut each other, they cut pieces, like we explained before when we started the class. They kind of interfere with each other in a negative way, where they cancel out each other to various degrees. And that's going to alter the frequency, it's going to alter the loudness, and so on. if you have pure tones and you combine them, you are going to get positive interference. So first, if the two waves are identical, exactly the same, you simply do not change the frequency. However, the loudness will be the result of the combination of the amplitudes of both waves. So that is going to give you an enhanced, a louder tone. And if they are systematically related, like one is half of the other, then they are systematically related. You'll cancel out in one end, but you will add to the other, so it will be like a partial interference. But what kind? Negative or positive? So you look at the loudness effect. If there's greater loudness, you say it is partial positive interference. There are situations when you have complete negative interference. For example, take this situation. Here is a wave, say wave A and wave B. So wave B goes this way. Wave A is 1 decibel, like louder. I don't know how loud, but it is obviously, if you say wave B is let's say 2 decibel, and wave A, let's say 3 decibel. So, but they are playing completely opposite of each other. So one, you have the rarefaction of wave B facing in the exact same direction as the compression of wave A. So when this compression is the molecules is gonna go back to the midline, and at the same time the molecule from B will be back to the midline, they collide against each other. So when they collide, wave B, that area of negative pressure, is going to absorb all it can from wave A. So because wave B has the capacity of, say, 2 decibel, it will absorb 2 decibel from wave A, and then there will be a little bit left to create a new wave. So that red wave that you see is what remains out of wave A. So you can see now, if wave A and wave B were exactly the same, they will cancel each other out, and then the sound dies. So that is complete negative interference. Let's look here. Wave A and wave B. Wave A is 1, let's say, again, I'm just giving random numbers. Let's say wave A is 4 decibel. Let's say wave B is 2 decibel. So how do we know that they're in the same frequency? You can look at here. This is where they coincide. The beginning is the same. The middle here, at the end of the first compression, it is the same. And then the end is the same. So the wavelength is exactly identical. So when you play them, they play at the same time in the same direction. So the compression of wave A faces the compression of wave B, and they push in the same direction. The frequency doesn't change, but the amplitudes, say 2 decibel plus 4, that's going to give me a wave that is 6 decibel. So the amplitude will change. That means the 2 waves will be longer, will be louder. Like I am singing by myself. Another person who has exactly an identical fundamental frequency like me says ah, and I say ah. Both of us, when we play that together, we will combine the loudness of our voices together, but we will sound exactly as one person. Now we no more just 2, if we are identical in voices. So the resulting red wave here in that situation is the same frequency, but it combines the loudness of both, and that is an example of complete positive interference. So let's look here. You have now different scenarios. let's say call this wave A and this wave B. So now wave A, the compression of wave A, coincides with only part of the compression of wave B. So when you look, make a line here, and this quarter of that wave, of that compression, is going to coincide with this quarter of this compression. So this piece is going to, when this comes back and this is going forward to the midline, you go here and here, and that will be enhanced. That will be enhanced because both of them are pushing in the same direction. So you could see here now, if this is, let's say, come to 1 decibel, this comes to, say, 1 decibel, you have 2. Now this becomes higher, the greater displacement. However, you have now canceled out that piece, and that canceled out that piece, and they create now a peak. So you kind of blend in this piece with that. Both of them have a greater loudness, and that is here, and this is the shape of the new half of the wave, of this wave and half of this. They combine together to create a different pattern. Okay, now let's look at the second situation, where the compression of the wave A is facing the opposite, is facing the rarefaction of wave B. So when you put them, play them from against each other, so this part that coincides here, this with this little piece, 1 wedge or 1 quarter here, coincides with this piece here. Draw a line down to here and draw a line up to here. So this piece will be taken out if this wave will be absorbed by this area of the compression here. So you basically have cut this length of this wave, and you have cut the length of the other wave, and then you have now combined this part here, when you cut it, is going to be just like that. And then the other piece here is going to combine in a similar way to the other, with the other part of this wave, and then you have a similar situation. So in effect here, when you combine waves of the same frequency, however, they are playing in the opposite direction, they can make each other interfere with each other in a negative way, and that will be an example of negative interference. That will make the frequency higher. It will make the frequency higher because you cancel out parts of these waves. Will be absorbed by the rarefaction. Okay, so here, let's take wave A, wave B. How do we know that they are identical or close to each other? Simply, the beginning is here, and you go up the same beginning. And then the end of the compression is the same line here. And then the end of this wave is, so what the situation here we have is 2 identical waves. A and B are identical. So when we play them at the same time, you have the energy, the amplitude of a wave B combined with the amplitude of wave A. And if this is 2 decibel, this is 2 decibel, you are going to create 1 wave out of the 2, 1 pure tone, but that pure tone will be greater. One thing that you could notice, for example, in the traditional way that they build a chorus to sing, a chorus, they look for people who have similar voices, So when they play together, their voices almost want to give you the impression that they are just one person, but that person is singing louder than any individual person. Okay, so in terms of reverberation, there is a video here that you can look at and see. There are also online, you can just Google reverb, and there are tools and machines that can produce different means of reverberation or examples. In reverberation, the distance is an increased distance between you and the barrier, like in a big auditorium. You feel that the sound is so deep and it is low frequency and it is like creating like a resounding sound when the auditorium is huge and big, because the sound takes a long time to travel and to hit the wall, come back to you. However, when it comes back to you, your eardrums will be still vibrating in response to the original sound. So we have now two tones. You make a sound, say hello, and that sound is going to go, like my room here has reverb as I'm recording. It has a vaulted ceiling, and the sound takes quite a bit to travel, come back, and you can feel the reverb in my as I'm speaking. So the source tone that I make is going to travel to a distance, and now my eardrum is vibrating in response. Now the reflected wave will come back, and before the eardrum stops vibrating, then the reflected wave will continue that vibration before the eardrum completely stops. Okay? Even though there are two different sounds, it's just the speed that the sound comes back because of a reasonable distance. And it comes back while the eardrum is still vibrating in response to the original tone. So that makes the sound stay longer in the air, and it makes it lower in pitch. Well, now, if you increase the distance, the farther away that you increase the distance, the more you move from reverb to an echo. So in an echo, you say, when there's a great distance, you say something, like if there's a deep cave, and the wave is going to travel and travel and travel and travel and travel and hit the barrier at the end of the cave. Then your eardrums have already stopped vibrating. When you say hello, your eardrums stop vibrating in response to your original tone. However, that wave that you made continues to travel in air as an independent sound after, and it hits the barrier, and then it comes back to you from the inside of the cave. By the time it comes back, your eardrums have already stopped vibrating for the original sound that you made. So that creates an additional sound that is called an echo. So an echo, again, occurs after the reflected sound wave comes back and after the eardrum has already stopped. And the reason it comes back, later is because of the long distance. There is a beautiful book called it's called Happy Birthday Moon. It's the children's book. And it plays on that, where there's a little bear goes on top of a hill and sees a moon, and he says, "Happy birthday, moon." And then obviously the hills, the sounds travel and hit the hills and come back. And the bear says, "Happy birthday." And then the sound comes back reflected, saying to him, "Happy birthday." So he thinks the moon is speaking to him. And the whole thing is basically about the effect of the echo. And it's, read it if you haven't, or you can find it on YouTube and listen to it. But it is a way to remember the difference between the echo and reverb. So what are the effects of reverb? If there is too much reverberation, that is going to cause distortion in sound. Children or individuals who have hearing loss, the children who have frequent middle ear infections, they will have difficulty with a reverb. If the room has a lot of reverberation, they already have difficulty integrating sounds and combining sounds in their brain, and the reverb is going to cause garbled, vowels, and a lot of sounds will be just, playing back and forth and causing a lot of difficulty. And this is part of what you do as an audiologist or speech language pathologist is to look at the room and evaluate, for example, if a particular classroom is suitable for a child who has hearing loss. So you go and look at the floor. You watch in the floor, do you have tile that is shiny? That could be a problem. It reflects a lot of the sound back. It can cause reverb. Is the room very big? Does the room have a door? What about the ceiling? Is the ceiling smooth and shiny? That will reflect a lot. Are the walls smooth and shiny? It will give you a lot of reverb. But in the other way, if you have a fluffy carpet and you have a lot, like a ceiling that has like a lot of holes and things, and the walls that are not, that could cause difficulty with absorption. So these rooms are evaluated by technicians, and when you go in, you examine and see the suitability based on the barriers that are out there, based on how much reverb or there is in the class, and then you can make appropriate recommendations based on what you know about reverb and the effects of absorption. Now, frequency is the number of vibrations that occur in 1 second. With frequency, when we speak about voice, how many vibrations occur in a single second? Always in a single second. So you can get a machine and say, okay, what is the frequency of this or that? Measure it, 500 hertz, 200 hertz, with a machine. You cannot, with your ear, when you hear the vibrations, you have no way of saying, oh, this is 200, this is 500. There is no way. But you have an estimate. You hear that and say, oh, this is high pitch, this is low pitch. So pitch is our perception of what the frequency sounds like. And we can differentiate between high pitch, low pitch, but we cannot measure with our ears a particular frequency and say this is 200 or 500 and so on. So frequency is the scientifically measured number of vibrations. Pitch is just a gross estimate. And you don't go and say the pitch of this is 100 or 2. No, you just say, well, this is high pitch, this is low pitch compared to another sound. Like the babies have a very high pitch compared to children. Children have a high pitch compared to adult females. Adult females have a high pitch compared to adult males, and so on. So always there's a comparison here. So the faster the rate of vibration, i.e., meaning the higher the frequency, and the higher that we perceive that frequency, the higher the pitch. Frequency is determined by 3 properties. We are now speaking, we are not comparing anything to anything else yet. When we speak now about frequency, let's look at 2 things, compare 2 different things. Okay, we are not comparing the same thing like myself. I want to raise my pitch. I want to lower my pitch. I'm not comparing myself to myself here. I am speaking about 2 different things. So, naturally, individually, when we take each element individually, things that have higher mass, greater mass, they vibrate at a slower rate. They have lower frequency of vibration, like this thick rubber band. When you pluck it, stretch it and pluck it, it will make a low pitch vibration compared to this one, for example, or to this one. So things that are more massive vibrate at a slower rate. They make lower pitch vibrations. Length, longer things by nature, when you, like a long guitar string, when you take it, pluck it, it will travel far away. When you let go, it will travel far away on the opposite end. But if it is a smaller string, it can't travel that fast. So the only way it is gonna do is to give you a higher pitch. So longer things are going to give you greater periods, greater wavelengths, but they will give you lower frequency, because that big structure, it has to take time in space to travel physically. So the rate of vibration is going to be slow, even though it covers a huge distance. Tension. Things that are higher in tension, that are more tense, will give you a faster rate of vibration, will be a higher pitch or a higher rate of vibration. So now these things, we take them in addition to comparing my voice to your voice and so on. I am going to compare my own voice to my own voice. You know, I have my vocal folds, like say they are, you know, often say, let's say they are like this. And I'm going to want to raise my pitch. The only way for myself to raise my pitch with the same vocal folds is to make them more tense. How do I make them more tense? Oh, I increase their length. So when I increase their length, that is going to make them, you say, but that's going to lower their frequency. But no, I am speaking about my own voice already before stretching them out. Before that, they were massive and they were slow in vibration. So if to increase their tension, I have to increase the length, but I will decrease the mass. So that will cancel out the effect of length. So when I pull, instead of that same rubber band, for example, that is thick, I'm going to pull it more and more. The more that I pull, the thinner the rubber band will be. So if you cut 1 inch of that rubber band, when it is stretched out thin, it will have less mass in it than a rubber band that is stretched that is not stretched as long. So in effect, again, for speaking about my own or your own vocal folds, how you make them adjusted to give you higher pitch is by increasing tension. How do you increase tension is by pulling them, by increasing their length. When you increase their length, you make the mass per square, centimeter, for example, you make the mass less. So you make the mass less, it makes the thing vibrate at a faster rate. So the human range of hearing, we can hear 20 vibrations. If they occur 20 vibrations per second, we can hear that. Then, if the frequency goes up to 20,000 hertz, we can hear that. But above 20,000, we cannot hear. And below 20 hertz, we cannot hear. So this is the range of frequency for us that we can hear, given that we have normal hearing. Below 20 hertz is called subsonic. Above 20 hertz is called supersonic. So in terms of speech, first, the auditory cortex, which is, I mentioned, in the superior temporal lobe of a superior temporal gyrus of the temporal lobe. And that area is organized in a way that the rostral or frontal piece of it begins with 20 hertz. And then as you keep going back, it goes to 20,000 hertz. So it needs stimulation frequently. Each area needs to be stimulated by getting familiar with the particular kind of tone that it needs in order for it to connect. And if the person doesn't hear these tones, frequently, especially during development, this area will not connect appropriately. And this can occur, the sound deprivation can occur as a result of frequent middle ear infections or hearing loss like sensorineural as a result of cochlear damage and so on. So the best range for human sounds is between, we'll come back to this later, but between 1,000 hertz and 4,000 hertz. Because most of the sounds that occur that are 1,000 hertz, the sounds that are 2, 3, 4, up to 4,000, these sounds don't require as much energy to be heard. Okay? Yes, you can raise any sound, but these are the sounds that can be heard at a lower amount of energy in normal circumstances. So in this shape, we say this is like the speech banana. We'll discuss it later. So now what is amplitude? We said the compression, the peak of the compression, that is the maximum point of displacement. That maximum point of displacement, we know it is the intensity, the amount of energy that is put to bring that thing to the farthest distance. And we know this as amplitude. So amplitude is the degree of particle displacement. How far do the air molecules get displaced? The more energy you put, the farther that they are going to travel. How many? Travel displacement from the original position. And it's the amount of pressure changes generated by the motion of the molecules of air. Now speaking about sound. Intensity is the amount of pressure per unit of area measured. Like your eardrum, how much pressure do the sound waves put into it? And based on the square centimeter space of it, and then you compare the pressure that's coming in, you can calculate. So intensity, again, the amount of pressure per unit of area. Like you stand on a table. Where is the maximum amount of pressure? It's under your feet. Every part of the surface of the table is going to carry part of your weight, but as you go farther away and farther away to the edges, the weight will be distributed, will be less pressure. So it is measured in watts, watts squared, or meters, or watts squared, or centimeters. So our perception of the amplitude and point of displacement, how we feel it, our perception is, we say, oh, this is loud, this is soft. So loudness is the same as amplitude, but amplitude is the real thing that you can measure with a machine. Loudness is your estimate of the amplitude. Loudness is determined by how much air that you can squeeze between the vocal folds. The greater the volume of air that you squeeze between the vocal folds at the glottis, the opening between the vocal folds, the greater that column of air is going, and the greater the pressure, the greater the loudness. Because, of course, you need a lot of energy to make that intensity or amplitude. So the situation goes that a sound, in order to increase the volume of a sound, loudness of a sound, to make it double, you have to put 10 times the energy that you put in the previous sound. 10 times. So if I say my sound is, let's say, for example, 1 decibel initially, and then I want to raise that to 2 decibel, I have to put the 10 times the amount of energy that I am burning in order to make the sound louder. So now I want to make the sound 3 times loud. Oh, then 10 is not going to be enough. I'm going to go to 100, and the 100 becomes 1,000. So in no time, you're going to find that the numbers are out of control. So there are 1 trillion intensities that coincide to 140 steps of loudness to make the sound louder from 0 to 1, and then 2, 3 to 140. You need to go through 1 trillion. units of intensity. So Alexander Graham Bell took these units, the trillion intensities, and he crunched them into equal spaces, and he gave us the decibel scale. The decibel scale, dB, B for Bell, decibel scale is basically 140 steps that shows the sound from the softest to the loudest. And you could see now examples of like someone breathing. That's at 10 decibel. You see, for example, the sound of a fridge, recharging. That is 40 decibel. The sound of an airplane flying, 130 decibel. So we take this and we make an audiogram. The audiogram is a chart that is used by audiologists to plot the hearing when they evaluate your hearing and how you can hear. So the audiogram begins with with a zero first. There's a zero here. That's most of us normal hearing is at 0 decibel. There is -10, -5, -10. The lowest is -10. Anyone can hear, but this is not quite the norm. So that is called hyperacusis. Like you hear more than, like your acuity is more than it should be, and that can cause interference and can cause problems. People who have this cannot concentrate and will be easily distracted by noises. So 0 is the norm, but -10 is you can go. Some human beings can hear sound like this. So if you have an oak leaf that hits the ground, you are not looking at it. When it hits the ground, you should be able to hear it. If you can, that means your hearing is perfect. If the, say, maple leaf is a smaller, softer leaf, it needs to be louder for you to hear it. So when it hits at about 5 decibel, then you can hear. The more that you need it to be louder for you to hear, the higher the decibel. Like you need to raise it more and more and more. So you can see this is inversed. So this is the speech banana I was talking to you about, where most of the sounds that the best sounds that don't need that can be heard at the lowest level of pressure, these are between 1,000 and 4,000 here. The other sounds, yes, you can hear them, but you need to put more energy into them. So if you look here, on the vertical axis here, you have the decibel from -10 and then -5 and then 0, and then you can keep going all the way to sometimes to 120 or 130. So if you count these units, you'll find 140 in some, but sometimes you find 100 and maybe it goes to up to 110. I'm going to explain the reason. So here, for example, there's from -10 to 120. We use that because if you need a signal to be raised by 90 decibel. That means you cannot hear anything. That means basically like having no cochleae. So this is an audiogram. It shows you the levels of hearing, and every level has a particular range. So from basically up to 20 decibel is normal hearing. Like if that oak leaf that you were supposed to hear at 0 decibel, if you can't, and then you put a microphone next to it or something to amplify the sound, so that you can, if you raise the sound to 10 decibel, that your hearing is considered okay. If you go 15 decibel so you can hear it, it is okay, it's considered normal. Even you come close to 20, then no. So normal range of hearing is from -10 to 20 decibel, that is the normal range of hearing. From 20 to 40 decibel, that is mild hearing loss. And from 40 to 70, that is moderate hearing loss. And from 70 to 90, that is severe hearing loss. And from 90 and up, that is profound. This person will not be able, like if it takes, you have to raise the volume of that oak leaf to 90 decibel for that person to hear it. That means that person has profound hearing loss and they cannot hear the sound at all. They basically can feel the vibrations of the sound through their body, but there's no way they can hear the sound. The lines that you see here, red is for the right ear and blue is for the left ear. Blue. So left ear is blue and right ear is red. And so, for example, I go and test someone to see when they can hear that oak leaf, for example. I make tones beep, beep, beep. The faintest tone will be like beep, like compared to the loudness of the oak leaf hitting the ground. The person can't hear it. So I'm going to raise the volume and raise the volume and raise the volume. And that person, it takes that person up to 30 decibel, 35, for that person to hear the leaf now with, amplification. So that means that person has a mild hearing loss. Or it could take that person maybe 40 decibels. So these marks are going to be down the chart. So this is what is called pure tone, pure tones. As the tones beep, 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 and individual tones that are. Now, what if the person has a problem in the middle ear or outer ear, like middle ear infections and so on? How do you determine that hearing loss is in the cochlea or the nerve, or it is in the middle ear? So what you do is you do something called bone conduction, where you get you put, instead of headphones, you put a piece of metal here and on this bone here, and it's called bone conduction. When you transmit the sound, it will be vibrating the skull and it will vibrate the inner ear directly, bypassing the middle ear. So now if the inner ear gives you here, it says here, and that this blue bracket is for left ear, this red is for right, and you compare, so, oh, the hearing is in reality in the normal range. That person's hearing is perfect. However, why do we get this from the pure tone? When we put the tone into the ear, outer ear, it means that there is middle ear infection or some kind of obstruction in the ear that is causing it to make the person unable to hear. And then you go and with intervention, you can cure that problem. So now you can see the effect of hearing loss that results from middle ear infections. The child will be sitting there acting like having a mild to moderate hearing loss that will wipe that child out, especially if there's a reverberation in the room or distraction or anything. That is going to have a tremendous impact on that child. Okay, now what is the acoustic reflex? And because when we speak about, I'd like you to know what the audiogram is, the different levels of hearing loss, and the difference between bone conduction and pure tone. Now, acoustic reflex is a pain threshold, the point where you start to feel pain if the sound is raised to a certain level. So for people who do not have a hearing loss, no hearing loss, you could raise the volume to 110, 120, even 130. And way they're fine. If you hit 130, they say, oh, the sound is too loud, it hurts my ears. Okay, now if you have the same sound, keep raising, and someone has a moderate hearing loss, for example, and you keep raising the sound. When it comes to 90 decibel, that person will be shouting, say, this sound is hurting me. So the pain threshold, the acoustic reflex, is triggered at decibel or even before for people who already have a hearing loss. And it is triggered when the sound loudness for normal people with normal hearing, to when the sound reaches 120 or 130 decibel. Now, why is that difference? Now, the ear is already having problems and experiencing damage, and it cannot afford more. So before the sound crosses the 90 decibel or something like that, then it just gives you that pain so that you can go and protect yourself and avoid that source that is causing you the damage, the pain. So the pain comes from that tiny muscle here. You see let me take the camera here. You see that little stapes as it is sitting on the oval window. Now behind the stapes inside of the oval window, there is fluid called the perilymph, and that fluid has nowhere to go. And the stapes is sitting here. When the sound wave comes in, it will push the stapes into the oval window, depending on how intense the sound is. And when it does so, if the sound is very, very loud and very intense, it will send it deeper in. If you do this all of a sudden, you can damage the cochlea. So as a protective mechanism, that tiny muscle here that is called the stapedius, because it is connected to the stapes, that stapedius, as soon as the sound hits the eardrum and it causes a lot of great compression, that will be felt by that muscle, and immediately it will contract, it will shrink, and it will pull the stapes to the side of the oval window. It will pull it to the side of the oval window. Of course, it has protection, and it doesn't, when you pull it, it is still attached, but it is flexible. So this way you can, that pain is going to cause you, or cause the pressure to be less on the cochlea. It will protect the damage against damage, and it will make you find ways immediately to do something. Put your fingers in your ears, do something. But this is why that acoustic reflex occurs as a result of the stapedius muscle contracting and pulling these stapes to the side of the oval window, and thus avoiding the pressure from going into the scala vestibuli. And we'll discuss this in the hearing section, but you need to understand it as it is discussed now, and to be able to describe what the acoustic reflex is. The acoustic reflex, don't say the acoustic reflex is when this is no, you need to define it in a scientific way. The acoustic reflex is the pain threshold. The body has lots of pain and all over, but you say in the middle ear, you have to localize it. The acoustic reflex is the pain threshold in the middle ear that is caused by an intense sound that reaches 120 or 130 decibel if your hearing is normal. Okay? If you come to that threshold, it will trigger the acoustic reflex. And for people who already have hearing loss, the acoustic reflex will be triggered faster. You will reach the threshold for these people will be about 90 decibel or even lower. Once you reach that, they scream. So know that, how to define it, and know the difference for people with hearing loss and people who don't have a hearing loss. I wanted to point out too, this muscle here, before I end, this muscle called the tensor tympani. You notice it is connected to the to the malleus, and the malleus is connected to the eardrum. So when there is a high-pitched sound coming in, the tensor tympani will will contract and will pull the entire tympanic membrane back, and that is going to make it more tense. It makes it able to transport or to carry the higher pitch sounds. When the sound is low pitch, that tensor tympani is going to be relaxed and the eardrum is going to be a little bit less tense. Okay, so now we have concluded the section, and now I'm going to tell you the questions I promised. Sorry, the video got longer than I had anticipated, but I wanted to clarify the concepts and make them crystal clear so you can go back to them and kind of find your answers there. So these are the questions, or the kind of the study guide, particularly for the previous unit, for the previous segment of this unit for part 1, and the lecture is available on YouTube. So you need to know the basic concepts that we discussed at the beginning of part 1. For example, what is acoustics? What is bioacoustics? What is density? What is all of these concepts? You need to understand them. You need to memorize them. What is sound? You need to provide a scientific definition of sound.